Okay, so today we're going to talk about a speed-up technique called pipelining. So last time we said that we had, our instructions had a fetch stage, a decode stage. So fetch is where we have the program counter goes and gets the next instruction, grabs the instruction back. The instruction then applies electricity and we start figuring out what it is we're trying to do. I think last class we had 4 stages. This class, just to make this point of pipelining, I'm going to add a 5th stage. So let's say we had a 3rd stage called reading registers. Then the 4th stage, like we had last time, was executing. And then the 5th stage also, like last time, was write back. Or write results. I'll say write back. So we're going to write our results back. Okay. So if we wanted to run 2 instructions like add, and I'm writing the assembler code, not the machine code. Add register 1, register 2, register 3. Add register 2 to 3 and put the results in 1. And then the next line might be subtract. Register 1. Register 6, something like that. Subtract register 1 from 4 and then put the results in register 6. So the first instruction, add, we would fetch the instruction, we would get its contents. This is a, like we said last time, this is assembler code for a machine code. So we would grab the machine code and bring it to the processor. Now the electricity starts flowing, that's the decoding stage. And then we can eventually figure out what it is we're doing. Now I basically took what we had last time, I think we just had an execute stage. So I just put in another stage where we're reading values from the register. We already know now we're going to be doing an add, but we're reading the values from the register to grab those. And then on another stage do the mathematical computation. So here there would be something like the full adder, the electricity flowing through to perform that computation. And then when we're done, some instructions have us write a result back. Some don't. So this stage sometimes has something to do and sometimes it doesn't. Each of these represents a piece of hardware and they're all wired together so the instruction flows through each of these. So right now it looks like we would use this piece of hardware, then this piece, then this piece, then this piece, then this piece, and the instruction is done. After this piece is done, we can now begin the next instruction, the subtract, right? So while this add is being done, like let's say we've fetched it already, we've decoded it already, and now after we've decoded it, so we've taken the bits, we know we've got to read this register and this register. We're going to allow that piece of the hardware to now read those registers. At that point, what are these 2 pieces of hardware doing? When we're in stage 3 of this instruction, they're not really doing anything because they've already kind of done their job. The executing stage where, let's say it was an add, so we're going to let the results ripple through a full adder. What is that hardware doing right now? That's not doing anything either. And the part of the hardware where we write results back to memory, where we put an address in memory and a value we want to store and then let it flow through, that hardware is also doing nothing. So right now, really, the only hardware doing anything, if we were at stage 3 of the add instruction, the only thing doing anything right now is the 3rd stage. The other 4 stages are doing nothing. So if we could think of a way to put those things to use, one thing we could do is we could, if we know what the next instruction is, let's say right now we're executing this line and our program goes on and on. If we could figure out what the next instruction is, we could start running it right away. We don't have to wait till the add is finished before we can start. Okay, now do we always know the next instruction? Is it always true that for any program that's running, the next instruction is the one right after it? That's not 100% true, because sometimes you could have like an if and else statement and you might jump somewhere else. So it's not always true, but it's true a lot, right? Maybe 95% of the time it's true. So what we can do is we can add in a new layer of hardware between each of these stages. Because what's now happening is basically these stages are all wired together. They're electronically wired together, and results are just flowing through electricity to the next stage, and so on until the result comes out the bottom. If we could put in, let's just say, a layer of D flip-flops, just so memory can come in and get captured, right? Just we apply electricity, open up the results, and then capture them, and then close it. Now the next stage can read from it anytime it wants. So we'll add a series of latches. That's really just not even a fancy word. It's a word for a collection of memory cells. So we'll add in between each layer a series of latches. And so the reason is we're preparing for when one instruction is at stage 3, the instruction right after it could be at stage 2. And we don't want, since that's using different registers, if the electricity flowing through flows so fast it starts hurting the instruction we're trying to do. So we don't want to do that. We want to have like a staging area where the previous piece of hardware can capture its results and we know it won't be read into the next stage. So it looks a little like we're going to slow things down a little because now we're adding in more hardware, which is more time for the results to flow through. But these things can open and close very quickly. Much quicker than, say, the time it takes to read a register or execute an add or subtract. So these stages will be much larger. But we're just adding in a new piece of hardware. So the electricity is still flowing this way. And we're kind of taking into account that we have the ability to predict where the next instruction is going to be. We could then start executing the instruction as soon as the first stage is gone of the current instruction. We could begin the next instruction if we knew exactly where it was. Okay, so instructions that normally might have looked like this, we might have had our timing. If we didn't use pipelining, we'd have fetch, decode, read, execute, and write. We might have our instructions go something like this. We might have the add adds on stage 3, the add is here, and the right part, that's the add instruction, and then we begin the next one, the subtraction, and so on, right? Now what our goal is to do, so these are, we'll call these cycles. And remember a while back, we made a piece of hardware called a clock that basically had, a bunch of lines coming out of it. And based on the speed of which electricity can flow through the hardware, this line would turn on, then this line would turn on, then this line, then this one, and back to here. It would just keep going like that. So and that gave us the ability to power each one of these pieces of hardware so it can do its job. When we apply the power, now all it has to do is read the results of the previous stage, so just a new piece of hardware. And we can have the clock running, and then the first and the add instruction would go stage 1, 2, 3, 4, 5. When that was done, then subtract goes 1, 2, 3, 4, 5, and so on. But what we're going to try to do now is go like this. As soon as the fetch part of the add has finished, and its results are written here, start the second one. This is the reason we want to add these latches. If the second one started and happened to run really fast, we fetched it really fast, its results might be written on top of the add's results, and that's not good. So we want to open this, let the results of the adds get captured here, then lock them. Now while the subtraction is doing its fetch and the add is doing its decode, they'll never, result of the previous stage would never overwrite something. So we wouldn't have this timing issue. Now we're going to try to do subtract. And now we're getting the output coming out, looks almost like 5 times faster if we have 5 stages. And actually, the more stages we make, so remember last class we said, the more stages we make, the quicker they will be. It might not have a total, a net gain. If you had 5 stages that took 2 nanoseconds, and you turned it into 10 stages that take 1 nanosecond each, well, as far as an instruction goes, it came out the same. But as far as pipelining goes, we're now doing an instruction per time it takes for a stage to run. So actually now we have an incentive to start making more stages that are quicker if this pipelining technique works. Okay, so this works great if we always can predict when the next instruction is. And if there was an instruction after this one, we'd put it here. Right? If we can always predict it. We're not going to always be able to predict it, but sometimes we can predict it. So, assuming everything is fine, suppose we'll go over an example. Let's say each stage in the unpipelined system, each stage in the red, let's see example. Each stage takes 25 nanoseconds. And the latches, this new thing, the latches take 1 nanosecond. How long does each instruction take now with the pipeline? So, it'll be the pipeline time. Cycle time, pipeline equals cycle time, unpipelined, so UP, divided by the number of stages, plus the new latency. So this is this is the new, the better version. So last time it would take 1, 2, 3, 4, 5 times 25. So it's 125 nanoseconds. Now how long does it take per instruction on average? This would end up being equal to cycles unpipelined I'm sorry, the cycle time would be 25 divided by the number of stages, which is 5, plus nanoseconds, plus 1 nanosecond for this delay, just to capture the results of the previous stage. So each stage takes 6 nanoseconds, when before they used to take 25 each. So the speed up, I guess if you wanted a percentage, it would be 25 divided by 6, so this would be how many times faster we're going? What would that be, 4?
Yeah,
4 point something. So we're going like 4 point something times faster doing this. Okay. So, looks good so far. And like I said before, we have to know exactly where the next instruction is. For any given instruction, we have to know where the next instruction is to get that kind of a speed up. Okay, so, a couple of things we have to consider. It doesn't work out so perfectly, but it still looks like this is an opportunity for improvement. Suppose we had an instruction where suppose we had instructions like this. Add register 1, register 2, register 3, and the very next line was subtract. Register 4, register 5, register 1. Okay. So, in this case, and what this means, I'll put a comment here. This means add register 2 and register 3 and put the result in register 1. So it's like, these are the two inputs and then that's the result. Okay, so then this means add register 5 and register 1. I'm sorry, subtract.
Yes, subtract.
Yes, subtract. Subtract, I guess, 1 from 5.
Sort.
Right. From register 5 and store it in register 4. Okay. So if we pipeline this, and let's say we're not considering the branching problem, which is obviously coming up, but if we knew that this was the very next instruction after this one, we started pipelining it, the result would go, I should have left the chart up before, so it's fetch, decode, read, execute, and write. So the first instruction, add, we do the add, it goes, do the add, and then we go and we do the subtract. There's a problem where whoever wrote this code, whether you manually type in assembler code or you wrote code in C or C++ or Java, and it compiled into these machine instructions, that these are the corresponding assembler instructions for. The intention was that this instruction this add instruction was completed before the subtraction starts, right? You assume, the assumption is this whole thing finished before this one started. Now this pipelining trick, which we're doing to try to make the program run almost 5 times faster, 4 times faster, has to make sure that there's no side effects that cause that to not be the case. So let's see. The value in register 1 computed here has to be, the computation has to be finished before we start this.
Yes.
When does the value get written to register 1? It gets written to register 1 right here. At this point in time. At time 5 is when the value, now with this pipeline trick, the value gets written to register 1. But as far as the subtraction is concerned, we're going to read register 5 and register 1. When do we read them? We read them here. So the read of register 1 is done at time equals 4, but the write of register 1 from the previous instruction was done after. If we're doing the pipelining thing. If we did it the old way, where we do add, then start, subtract, we have no problem. The results will come out good. But here, we're starting, we have at time equals 1, we've begun the add. At time equals 2, we have the instruction for the add, and we're now decoding it. And we're, at the same time, we're feeding in the subtract, the first step of, we're fetching the subtract statement. At time 3, the subtract statement is being decoded, and the add statement at the same exact time, both pieces of these hardware are now running. We're decoding the subtract statement, and we're also reading register 2 and register 3. Those values are now being read into the ALU. At time equals 4, we're now performing the computation. We're adding, we're actually taking register 2 and register 3 and running them through the full adder to compute the result of those two numbers added together. So at stage 4, the result is being calculated, hasn't been written to register 1 yet. It's just being calculated. We don't even know what the number is yet to write to register 1. But at time equals 4, the add instruction is adding what it read from register 2 and register 3. Those two values are now being added together. And at the same time, we are now reading register 5 and register 1's value to prepare for the subtract. And the problem is we're not reading the value that this one is going to store. We're reading the old value.
Okay.
So let's say if register 1 equals 1, register 2 equal 2, register 3 equal 3, we would want register 1 to become 5. Right? Register 2 plus 3 gets added to 1. We would like it to become 5 before we read it, and then we'd like to subtract 5 from register 5. So let's say register 5 was 10. We would like register 4 to become a 5. 10 minus 5 is 5, something along those lines. But the problem is that when this was a 1, we've added these two numbers together as we were executing the add. As we were reading at this time, as we were adding the two numbers together, we were in the process of adding the 2 and 3 together. We haven't figured out the result, and we haven't written the 5 here yet. We're just in the process of adding them together.
Just reading it.
We then went and read this value of the next instruction. So we ended up reading it wrong, and we ended up doing 10 minus 1 is 9. So if this was register 4, we ended up with a result of 9, not 5. You know, something like that. So this is what's sometimes referred to, so now we have what we're going to call pipeline hazards. So pipeline hazards are when you get different results because you pipeline them together as opposed to running them on a, the slower way, the non-pipelined way. So this is sometimes referred to as, that one we just did was referred to as a read after write. Right, the first line was trying to write something. No, that was, we're reading the value. We're reading it before it was written.
We're reading in.
So we're writing after we read it. So that's right after read. Right after read. W-A-R. That's a W-A-R. We call these hazards. These are pipeline hazards. So there's a W-A-R. So that's the one where we're writing a value after the following instruction has read it, and that's a problem. We need to do the whole instruction first before the next one starts. We're doing this pipeline thing to speed things up, but we don't want results coming out bad. So what other kind of, I guess there'd be 3 other combinations. There would be write after write. That's a W-A-W. Now where's that a problem? Where one instruction goes to write something, and then another one, and we're assuming, I guess it's possible we could have read after write and write after writes together. But if we had just a situation with a write after write, would that actually be a problem for us? Now with the stages that we have, the writing is always done on the last stage. So if one instruction wrote to a value, to a register, and then another one right after it wrote to the same one, if we do a write after write, it's implied we're doing it on the same register. So whenever you say we have a, for example, if you say we have a write after read problem, you're writing to a register and then reading from the register, the same register, 2 different consecutive instructions. Since we happen to have our write stage as the very last one, write after write won't be a problem for us. However, if we decided to take some of these stages and break them into sub-stages, so we can get like 50 stages so we get a better result pipelining-wise. If we broke the write into like 4 or 5 different write stages, and one instruction is going to write to a register and another one's going to write to the same register right after it, then within those stages of writing, you may have a conflict. So write after write does not affect us on this processor, but we need to keep it into account in case we make a different processor where it would matter. Also, if there are any stages after a write, I don't know what that could be after a write, because usually that's the final thing. You do something and then you write the results back. But if we added more stages, if there was some kind of bookkeeping we wanted to add to it, then we could have, a situation where, like, if we check something that we've written before we can, like, if we had a database application where we write something and then the next stage is to check that the data is valid or not valid, then another instruction right behind us writes and changes our results. So then we could, on a different processor, have a write after write problem. What else is there? There's read after write. Well, that's an R-A-W issue. So if we read a value after it's written, again, on our particular architecture here, this won't be a problem, because the last thing we do is write. So if somebody was to read something after it was written by a previous instruction, that previous instruction has done whatever it needs to be done. So any reading done after that would not be a hazard on this one. But if for whatever reason we had read instructions that came after write, or if the writing phase broke up into 3 stages and then we could be reading while writing is still in progress, that could become an issue. And then also read after read. Read after read. Could this ever be a problem on any architecture? If you read from a register and then the very next instruction also reads from that register, but no writing to that register is done. So this one should never a problem. This one, these two would be only if the write stage was expanded. Whereas if the writing part took 3 or 4 steps, then if reading needed to be done, we couldn't count on that the writing had finished, because not all of its steps had been done. And this one's a pretty common issue. You have to worry about this, the write after read. You have to worry about that one. Anytime your writing stage comes after your reading stage, which is pretty much every architecture is going to do that. So you want to add 2 numbers together, first you have to read them, then you have to perform the math, and then you write the result. So there'll always be a writing stage after a reading stage, so we always have to worry about that one. So suppose we had this problem. Let's go back to just this problem. The write after read one. And suppose we had, with this architecture, suppose we had fetch, decode, read, execute, and write. And we wanted to pipeline these. But now as we're loading them into the pipeline, we're noticing, as we're getting the instruction, we know what type of instruction it is, read, write, or whatever. And we're loading them into the pipeline. If we said add we're going to start with the subtract. We're going to decode it, and once we realize that, at what point will we realize we have this write after read conflict? It would come, well, where would the problem start? The problem would start if we started reading the register that hasn't been written yet. So we don't want to see sub here, because that's where the damage is done. The sub on the read stage has to be after the write of the add. So we would want sub here.
And then would that push back, that would obviously push back the execution and the writing of the sub as well?
Yes, but we won't know, the hardware won't know that there's a problem until we decode it. We have to know, okay, this thing, so basically the fetch stage, we're just getting the bits of the instruction, loading them into the instruction register. The decode is where we now say, okay, this thing needs to turn, this is going to do a subtraction, it's going to read some certain fields, and we know that the write of register 1 has not been done yet. So we can still do the sub decoding, But at this point, we now have to put a stall. We have to now stall that instruction. So this is time 1, 2, 3, 4, 5, 6. We're now going to have this stall. I should write that in a different color.
And then it'll be 2 stalls for the execution and then 2 stalls for the write for the sub as well?
Right. Because now the sub would go this way. Yeah. So there'd have to be 2 stalls on every, there'd have to be 2 stalls between, I guess, starting at this point, there'll always be 2 stalls between, an intentional gap was made. So when we're doing our equation of how much we speed up, now there's going to be some stalls along the way for these types of hazards. There's also another type of hazard would be what they sometimes call a structural hazard. This is, again, where we're going to have to put stalls in. So really, when we put a stall in, what we're basically doing is saying this piece of hardware will now do nothing and will wait. So it's the electricity that's saying, do this step, then do this step, then do this step, then this. If we stall a step, we'll have to run a 0 bit into an AND gate so that even if the electricity is saying this should do something, it will get zeroed out and nothing will get done. And then once it turns back on, it'll pick up where it left off. So, and like I was saying before, there's such a thing as a structural hazard. These were pretty popular 30 years ago, but all the architectures are trying to get rid of this. But if you remember when we talked about the processor, we said the processor we went over in this class, we said was really simple and had some flaws in it. But if we wanted to write, like we had 16 registers, if we wanted to write a result to the register, we would put the value we want to write and the particular register we want. We'd say like, write a 2000 into register 4. If we want to read from a register, we were using the same buffer. We were saying we could read it, we use the same memory address buffer and the same memory address register and memory address buffer. The one that said which register and which value. We were using the same 2 ones, whether we were doing a read or a write to a register. That means we can't do a read and a write at the same time. So that, like I say, the architecture we went over when we were talking about processors, it was a very poor design, but it gets the point across. So that was designed so poorly that you can't even do a read and a write at the same time. So we couldn't even do pipelining with that processor because we could only read or write to the memory, the register bank one at a time. So obviously if we designed our hardware where you can read into one spot while writing from another spot, there'd be no issue. So every processor does that now. But then there was the idea of what if you simultaneously wanted to read and write from the same register? So suppose we were reading and writing from the same register, the step that was doing the reading, and then 2 steps later something else was writing to the same register. If you remember, we would open up the register we're writing to, and we would say of all the registers, let's read from one register that goes through a big OR gate. We could actually, the result where we are writing to the register might flow right through back down to where we're reading from. And then that could either be considered a structural hazard. So structural hazards are basically, because of the design of your processor, 2 of these steps cannot be done simultaneously. Or if 2 steps were being done simultaneously, you might not get the same result that you want. But the structural hazard concept's starting to go away because all the processors are designed. That would be basically a flaw in the design of the processor that it can't handle pipelining, but since all the processors are being done for pipelining, you can come in if you want, use the computer.
Yeah.
Yeah, that's fine.
Thanks.
Okay. So, yeah, so those are kind of going away, but if there is an issue with the way the processor was designed, certain steps might not be able to be done at the same time. Like a pipeline. Okay, so now, what if our instruction said, what if after the add, let's say we did an add and a subtract. No, forget subtract. Let's say our instructions are now, we have a branch instruction. So if our code was add, register 1, register 2, register 3, and then branch not 0, register 1, 2, and then some label. Label X. And then somewhere later on in our code, there was label 1. So this is basically saying, add register 2 to register 3, store the results in register 1. If register 1 is, let's say not 0, let's say we had an instruction, a branch negative. If register 1 is negative, we jump down to here. If branch 1 is not negative, then our next instruction, let's say subtract again. Subtract, and then, register 4, register 5, register 6. But if the register is 0, is negative, then we want to jump to here. Okay, so as we're pipelining, yeah, we got the branch 0. Branch negative. The add keeps going. The branch 0 would go till when? We read, are there registers that have to be read? Yes, we have to read register 1. Now, we're also pipelining the subtract. So I guess the assumption, we could flip a coin, but either this instruction or the one that appears here is going to be the next one. Because we may branch or we may not. So let's take the guess that we're not going to branch. So now we can start pipelining the subtract. Now, the add is going to, of course, be done. We have a structural hazard. We have we're going to read this number before this one is written, so we actually need stalls to happen. Because we need to know what the result is before we even decide whether it's negative or not. So where did that stall come from?
Two stalls.
Yeah, we can't do the reading yet, so we're going to have a stall here. Up to here, we're fine. We're reading register 2 and 3. The branch not 0 knows it needs to read register 1, but we have to detect that register 1 is not set yet, so we'll stall.
So we can execute.
So, now I'm getting.
It's the third one down.
This one should be stall.
Stall.
Okay, and we have to stall it twice, right?
It has to be written before it can read in.
Right. And what about the subtract this line? Which I'm obviously gonna intentionally say, no, we're gonna jump here, so this is gonna be a wasted step. We still have to be, we haven't even decoded it yet, right? We're stalling the read piece of hardware, but this can still decode. That's not a problem yet. Now we have to stall again. The read piece of hardware has to be stalled again. Stall. Yeah, after 2 stalls were okay. And then what? The branch can start right after. Now the value is set, so the branch can start here. The branch not, a branch negative instruction can start up again. The subtract is now, has gone through 2 stages, but it's getting stuck. Because this piece of hardware was delayed because we needed the result. So the branch starts, nothing's done here. Then the subtract starts. Subtract starts its read step. So it's now starting to read register 5 and register 6. The branch then executes. So that's now looking at the contents of register 1 and to check if something's negative. It's just looking at the high order bit. That's a very quick step. And realizes it needs to jump somewhere else. So it's right, there's nothing it writes back. There's no write back step, but we can still say it's in its write back step. But it now changes the program pointer to point to this program. And this, well, we're already up to, well, we're now executing this. We don't want to execute. No, we're not writing the results back, so it's not too, we now would have to detect that this looks a little dangerous, but we're executing the subtract. We could get away with this in this particular architecture. We don't want the result back. We don't want 6 minus 5 being written in 4. It wasn't meant to happen. So for it to have gotten this far is a little dangerous, but now we have to cancel this instruction. And canceling the instruction, the only effects are the write back. If you do an instruction and never write any results, it's like you never did it. So we just got to make sure, in this particular architecture, we just want to make sure we don't write any results. That would be like it never happened. And then, now whatever instructions appear right after here, they're going to start getting pipelined. Those steps are going to start. But when we jump to this label, we have to make sure none of the writing steps of any of these instructions got done. So it's kind of like everything from subtract onward, just none of those instructions completed. So, and then whatever the new instruction here would then get loaded in. So we'd end up with, so we're having some stalls here, and then we also have some instructions that start executing, but their results never get written. So those end up being like wasted time too. And then if we wanted to calculate what the real value is to pipelining, we'd have to say something like, we'd have to have a percentage of how many stalls we had, and then how many wasted instructions, and subtract those out from our results.